Hello, my name is Schuh, and I'm here on behalf of Claire Maiza, Joël Goossens, Pascal Raymond, and Benoit Dupont de Dinechin to present you our work entitled A Study of Predictable Execution Models Implementation for Industrial Data Flow Applications on a Multi-Core Platform with Shared Banked Memory. So to begin and give you a context of our work and what we want to accomplish, our main goal is to construct correct by design time predictable programs, which means that they will behave the same no matter what the hardware where they are executed on decides to do at runtime. These programs typically come from the data flow domain and are coded with synchronous data flow languages such as SCADE, which is our starting language on this work. We also want to run these programs on multi-core platforms, which are inherently subject to interference that comes from the multiple cores accessing shared resources at the same time, such as the memory. Our approach to construct such time predictable programs is to have a global static scheduling between all the tasks on the system, and we want to release them at precise times. So we do a time trigger execution of the tasks on the system, and we don't allow any preemption between them, thus avoiding cache-related preemption delays. Our target platform is the Core MPPA2 processor, which is known to be a good architecture for time-critical systems. Highlighting the main contributions of this paper, the first one is a technique to implement SCADE applications inspired by predictable execution models. We have selected a handful of variants of PREMs that we have found in the state of art and chose to implement some of them and some variations, changing the number of phases, how the memory is partitioned, and how it is accessed, if we allow interference or if the memory is accessed in isolation. And for the case of isolation, we have developed 3 new global scheduling algorithms. The second contribution is a comparison of the selected and implemented execution models, and we have found that a 2-phase model behaves the best. We've seen a 32% decrease in comparison to 3-phase models. We have also found that bounding interference is better, seen in average a 26% decrease in execution time in comparison to the same execution models implemented in isolation. And the third contribution are guidelines for predictable implementation of data flow applications. To start the introduction and state-of-the-art section of our presentation, we'll talk about data flow applications. These are programs that can be represented and seen as oriented graphs composed by several nodes, which are the computational units of the system performing a wide variety of tasks. These nodes are connected through directed wires that represent the communication between them and also their data dependencies. These applications are coded in these high-level synchronous data flow languages and are typically used for critical real-time systems so that the system's engineers can focus on the functionality, and then the low-level code generation can be certified later on in the process. And this is what happens typically on the majority of the code run for control on planes. And as our target platform is the MPPA2 processor, we are particularly interested in the parallel code generation from these high-level data flow languages. We use for that the SCADE multi-core code generator, or MCG, that compiles the nodes of the system into classical sequential tasks, but decouples the communication part from these nodes and generates an intrinsic read, execute, write model from them, allowing us to map and schedule these different phases of one node independently of each other. Our target platform, as already stated, is the Core MPPA2 processor, and particularly one cluster of this processor. Cluster of the MPPA2 is composed of 16 cores and 16 memory banks that are independently arbitrated. This helps to reduce the interference that we have on the system when accessing the memory, and also ease the implementation of isolation when accessing the memory. It is also said to be a timing compositional architecture, which means that it's a viable candidate for modeled interference analysis. And we also have access to low-level timers and performance counters to implement our time trigger execution and also do any measurements required by our workflow. We have also done a short survey on the state of art on predictable execution models, and we have found mainly two classes of works. The first one are works that perform execution partitioning, and here we have found that they mainly split the execution into two phases with an execute write model, or three phases with a read execute write model, and in particularly for the three phase, a memory centric one where we have a master core that manages all the memory accesses. The second class of work is the one that do memory partitioning, and some of them do not allow any interference on the system and run all the memory access in complete isolation, while others try to analyze and bound this interference, trying to compute shorter execution times. We were inspired by all these predictable execution models that exist in previous work, and we have selected some of them to implement and investigate. And for that, we have developed a simple data flow application that is shown here, composed of 5 nodes, and that is mapped onto cores on the system. Here, nodes are a terminology that comes from SCADE, but can be seen as tasks on other domains. And according to the execution partitioning, these tasks can be composed of 2 or 3 phases. So here we have the studied models that we have selected from the state of art and how we implement them on our platform. The first thing to know is that we have assigned cores to specific memory banks. So we can see here in the 2 phase, for example, that the green core is assigned to the green memory bank, and the same for the yellow core. In this 2 phase model, all the execute phase is run locally, only accessing the assigned memory bank. And the write phase can actually access memory banks belonging to other cores, and thus provoke interference. The next model is the 3 phase one, where we have the same execute phase behavior. We add a read phase, but we also have now a global shared bank memory where all the read and write operations access. So we potentially have interference coming from any read or write operation. And the last studied model is the memory-centric 3 phase, and here we have the same behavior for the execute phase, but now we have a master core that sequentializes all the memory accesses to this global shared banked memory. So interference is not possible, as we'll see later on. Moving on to the memory partitioning scheme of the studied models, I recall that we are seeing the schedule of this example, and we are particularly interested in how the write phases of N1 and N2 behave as they are mapped to different cores, and they try to both write to the N4 task, possibly at the same time. For the 2 phase model, we can have interference happening, or we can run all the memory phases in isolation. And here, as the write phase of N1 and N2 write to the same memory bank, we have interference happening, and they do slow each other down, which is represented by these red squares in the image. When we want to run them in isolation, we actually delay the start of the write phase of the task N2 up until the end of the write phase of the task N1. So we don't execute them in parallel and we avoid any possible interference. For the three-phase model, we have the same behavior, only now we have a global banked shared memory, and we possibly have interference from any read or write operation that targets the memory. So here we can see that we have interference when the read phases of nodes N1 and N2 happen, and also on the write phases. And the same thing for implemented isolation, we delay the start of one of them up until the end of the other, so we don't have any memory phases happening in parallel in multiple cores at the same time. And now for the memory-centric three-phase, as I've said, we have a master core that serializes all the memory accesses on this global shared bank memory. So interference is not possible. And we can see here in the isolation schedule that all the memory phases run on this master core and they run in isolation. So in order to properly schedule all these tasks that run on the system, we need to compute their appropriate release dates. And for that, we use a tool called Multi-Core Interference Analysis, or MIA, which is free and open source, and has a model of our target platform memory system, the MPPA2. It basically takes as input the worst case execution times, or WVCT, of the tasks, and their respective worst case number of accesses, or WVCA, which are the instruction and data cache misses. And then it outputs the worst case response time of the system, or WVCRT, and the specific release dates of each one of the tasks. And a little detail about our implementation is that to enforce isolation, we include additional dependencies between the memory phase tasks. We finally arrive at our implementation workflow. This image represents all the tools that we use to implement our technique, and we are particularly interested in these green puzzle pieces that are the code that we will generate for the different memory phases, and also the architecture specific part. We start with SCADE MCG that give us the code of the execute phase and also an initial mapping and scheduling of the system. And then according to the execution partitioning model that we choose, we go on to the step 1 where we generate the memory phases. It can be 2 or 3 depending on the execution partitioning model. Then we give both of these codes to a timing analyzer, or we measure their execution and we obtain the WVCT and WVCA of them. We can move on then to the step 2, where according to the memory partitioning model that we choose, we either implement the task set allowing interference or incomplete isolation. And if we implement it in isolation, we need global scheduling algorithms, in particular for the three-phase model, where we need to coordinate all the read and write phases. MIA computes the release dates of all the tasks on the system, and we finally arrive at the step 3, where we generate the orchestration code, which is completely platform specific. Now we'll move on to the global scheduling algorithms required to implement the memory partitioning model in isolation. So the first thing to know about these algorithms is that they act on a memory transaction level. I've talked up until now about memory phases, and for instance here in the node N0, we have a write phase, but we have two memory transactions. We have N0 write to N1 and N0 write to N2. And all these three algorithms actually perform the decision about scheduling at this transaction level. This first algorithm is called three-phase contiguous because we consider the memory phases as a contiguous entity. Once we have scheduled a write transaction, we need to schedule all the remainder phase of this transaction, and then only if possible we will schedule the corresponding read transactions in the same order. So here we have an example, and we are actually precisely at this decision point where we have already the N0 execute phase schedule, and we must decide about the schedule of the memory transactions following up this execute phase. Here we have the memory transactions that are going to be scheduled and our algorithm. And it starts basically by scheduling N0 write N1, and then as it has to schedule the remainder of the write phase contiguously, it will move on to N0 write N2. And then it will follow up in the same order for the read transactions. Now moving on to the second algorithm, we call it three-phase optimized because we remove this contiguous constraint on the memory phases. We add the possibility of having idle time between the memory transactions belonging to a phase. And this aims to unblock execute phases belonging to other cores earlier in the process. So here we have the same example, and we'll start by scheduling N0 write N1. And at this point, we still schedule N0 write N2, but instead of following the same order for the read phases, we give preference to read phases happening on other cores. So we have N2 read N0 that happens on core 1, and this is going to be scheduled first to unblock core 1 and allow it to execute any execute phase that it needs to perform, and then we schedule the transaction N1 read N0. The last algorithm is the memory-centric one that behaves a little bit different because now we have a master core that is responsible for all the memory accesses on the system. As we can map these memory transactions to this master core, they can be arranged in any order that we want if we still respect the data dependencies that come from the data flow model. So here we have the same example, and our main goal here is actually the same as the algorithm 2, is to unblock cores that will run execute phases as soon as possible. So here we start with N0 write N1, but instead of contiguously scheduling N0 write N2, we schedule its mirror transaction, which is N1 read N0, and we unblock core 0 to execute any other task and leave its idle state. And then we follow up scheduling N0 write N2 and its mirror read transaction. And all of this happens on the master core, and we try to unblock the other cores as soon as possible. Now moving on to the results of our paper, we have selected 3 case studies to test and evaluate our workflow. The first one is the simple data flow example that we have seen up until now, composed of 5 nodes and mapped to 2 cores. And for all the case studies, we have added their computation communication ratio, or CCR, that reveals where the program spends most of its time. And for the simple data flow, it spends almost the double of the time communicating rather than computing. Second case study is the RTSS avionics on a RA program that has 10 nodes and is mapped to 8 cores. And we can see from CCR that it spends the vast majority of its time computing. The third case study is an automotive electrical compute unit program, an industrial use case that has 9 nodes and is mapped to 6 cores. And from its CCR, we can see that it spends the double of its time computing rather than communicating. Here we have the results of the simple data flow program. And the first thing to notice is that the blue bars represent the measured execution time on the platform, and the red ones, the theoretical worst case response time computed by MIA. And they are close for all the variants because we perform a time trigger execution. And actually the only difference between them may come from the last task finishing earlier than its worst case execution time. Comparing the different memory partitioning models, either allowing interference or in isolation, we can see that the two-phased with interference has lower execution times than the two-phased in isolation. And the same thing happens for the three-phase with interference if we compare with all the three-phase models in isolation. And now comparing the execution partitioning models, if we look at the two-phase with interference against the three-phase with interference, we can see that the two-phase has lower execution time, and the same thing happens for the isolation. So a two-phase model is always better. And comparing our developed global scheduling algorithms, we can see that the three-phase optimize behaves better than the contiguous and the memory-centric versions. The same thing happens for the RTSS and automotive case studies. We have the same tendency on their results. Only on the automotive use case, we can see that the three-phase optimized global scheduling algorithm actually behaves a little bit worse than the memory-centric. So we can see that they are not comparable, and they actually depend on the application structure and its CCR profile. Now, moving on to the discussion and some open questions that we can raise from these results. All our methodology here is based on the timing compositionality property of the architecture. And a proof of the existence of such timing compositionality has not been yet developed and could greatly benefit all the works that are based upon the worst case response time computation of a system. We have also seen in our survey that the three-phase model is more commonly used in the real-time community, even though our results show that the two-phase model is more efficient and sometimes easier to implement. In our case studies, we have also seen that the potential and the delay introduced by interference is really small. So all the global scheduling algorithms needed to implement the isolation memory partitioning model may be an overkill if we look at the actual interference that happens on the system. And now reinforcing the key takeaways of our paper. The first one is that taking interference into account leads to shorter execution time. The second is that a two-phase implementation is always more efficient than a three-phase one, no matter the memory partitioning model. And the third is that between the algorithms that we have implemented, our optimized version yields the best result in most cases, even though it is not comparable to the memory-centric, as we have seen for the automotive use case. So thanks for your attention. And if you have any questions, I will be glad to answer them. you can find me at the following email address, and you can find more information about me in this webpage.